So here we go, Michael.
All right. Thank you very much. Thanks, Robert, again for the.
It's just one slide.
Yeah, why not? Thanks again for the invitation. Thank you for having me today. Since I only have 2 minutes, I'm going to keep it short and let's really get started. So let's start by imagining a world where the most complex business challenges are solved effortlessly, revolutionizing whole industries and our everyday lives. That's the world Aqarios is building. My name is Michael. I'm CEO and co-founder of Aqarios, a quantum computing startup and spin-off from the LMU here in Munich. With more than 7 years of experience in quantum computing research, not quite 10 years, sorry about that, Robert, not one of these people. But with collaboration with numerous industry partners, we see ourselves uniquely qualified to be pioneering in leading this quantum revolution. The problem we're addressing is the complexity of actually applying quantum computing. So while quantum computing does hold immense potential, it remains out of reach for most companies due to its enormous intrinsic complexity. We're developing Aqarios Luna, a platform that simplifies quantum technology application with a focus on solving optimization problems. We here handle all the technical details, making quantum accessible to everybody. We see it as our mission to democratize access to quantum computing, hardware, and algorithms. We bridge a gap from quantum computing research to real-world applications, making quantum accessible to everybody. Our platform allows to easily upload optimization problems, automating the transformation into quantum-ready formats. Our AI-powered recommendation engine suggests tailored algorithms and hardware solutions. We cover everything from the problem definition to a quantum solution. Going to wrap it up. In a world where quantum computing seems inaccessible for many companies, Aqarios is leading the charge, turning it into a reality for individuals and industries alike. So join us in the quantum revolution and let's together redefine what's possible. Thank you very much for listening.
Thanks, Michael. Next, John.
Actually, let Phillip Weinberg here start off.
Phillip or whoever wants to do that.
Hello. Yes. So my name is Phillip Weinberg, and this is my colleague John Long. So we're here coming from QuEra to introduce our new SDK written in Python, Bloqade, which is our software for our neutral atom platform. And so our poster, basically, we will talk a bit about like what our platform is, what you can do with it. So we're not necessarily a traditional quantum digital, I guess, platform for doing quantum computing. This is this analog platform. And so because of our unique technology that we're offering, we have to offer a unique SDK experience. Next slide. In this poster, we'll talk about the features that we have in our neutral atom SDK, namely the analog interface between our QPU and the users, the user experience, as well as the basic features that we have. So, for example, we have parameterized pulse sequences and advanced visualization, and the ability to target multiple different backends. So please stop by, give us a chat, and we'll talk to you about our SDK.
Then we've got next. Here you go.
Hello, I'm Christian. I'm with neQxt, and we're a spin-off from the research group of Professor Ferdinand Schmidt-Kahler from the University of Mainz. We have about 20 part-time workers at neQxt and more than 30 years of experience in quantum computing. And we build our traps in-house and offer quantum computing. So both running on a simulator as well as on actual trapped ion hardware. And my poster is about the software stack that we've built to enable people to remotely access our quantum hardware. And we have our own compiler stack, and I guess there are quite some experts here who I want to talk to, or who I'm looking forward to talk to, and he might also want to talk to us. And so our main application, like for most quantum software researchers, is currently the variational quantum algorithms, so hybrid quantum computation. And I would like to discuss our flow and our access possibilities with you. Thanks.
Hello everyone, my name is Ricky Young. I'm the Chief Operating Officer at qBraid. You may have heard us before. It's awesome to see people from QuEra, as well as some of our other partners. We are building the Quantum Ecosystems platform where everyone's quantum software, as this is a pitch for Quantum Software Forum, can be on this platform and be available to anyone within a few clicks. So some of our partners that we have, of course, QuEra. We also are the other provider for Intel Quantum SDK. So if you're interested in trying that out, we have that available. Of course, we're also connected with other providers as well. So you can actually use our qBraid SDK to write your circuit in Qiskit, Cirq, Bloqade, Chasm 2 and 3, as well as other frameworks, and actually target other devices that are gate-based as well. So with that said, the qBraid team is looking to hire as well, and we also have some exciting work with Q4Bio, once again alongside some of our friends at QuEra. So we'd love to get to know you guys, and we're super excited to be part of this conference. Thanks.
Thank you.
Thank you, Rob, for organizing. My name is Stefan Hillmich. I'm here with the Software Competence Center Hagenberg. And I think we have identified one need that we didn't address so far. We all believe that the quantum revolution will come, but not every company is able to invest in a whole department that focuses on research and how to apply this. So we try to make this available for small and medium-sized enterprises as well. In this context, with the focus on Austria and on Europe. Next slide, please. In this sense, we envision some kind of framework where we have a set of industrial use cases and we can go with them from the left to the right, identifying which problems are applicable for quantum computing, which lend themselves, and of course, which are not applicable for quantum computing, because we believe this is important as well as not to overhype our technology and fall into the next quantum winter. The end result would be some kind of database in the heads of persons that work with us, and also a click or searchable online for companies to see is quantum right for them. And if you have use cases, I would be very happy to talk with you. If you have the software, obviously, or otherwise you wouldn't be here, I would be very happy to talk to you. So please check out and come to our poster and talk to us. Thank you very much.
Hello, my name is Pavel. I come from IQM, where we build quantum computers, and I work there as a software engineer in a design and simulation team. And I have a poster about KQ Circuits, a tool that we use in our company, but that is also publicly available as open source for everyone to try out or to fork it or whatever they want to do with it. Our tool, starting from this, taking a look at the entire design process of the QPU.
Sorry.
Yeah, no worries. Starting from the stage where you have already figured out your Hamiltonian and your circuit, then you can start designing the geometry that you need for your chip to implement that circuit. And starting from there, KQC provides aid for that. We have a library of all the elements, or at least the most used elements that you might need in your superconducting qubits. And we provide aid to then export that into a mask layout that you can send into fabrication. Or before you want to fabricate, we also provide support for exporting that geometry data into simulation. And we support multiple third-party simulators for you to do this simulation on your designs. So everyone is welcome to check out my poster, and also there is a live demo opportunity available there to try out on my laptop on different things you can do with KQ circuits. So,
Cool.
Thanks.
Thanks a lot.
Hi everyone, my name is Giangiacomo Guerreschi, and I will present today the Intel Quantum SDK. So first of all, just to mention, this is readily available to everybody who sign up to Intel Developer Cloud. This software can pre-installed, so you can immediately start playing with it. Of course, there is a team supporting. So what can you expect right from this? There is a current release, something that will be updated by the end of the year, and then there are some future plans. So the current release is a full system stack, quantum computing system stack in simulation, meaning that the final backends will be a classical software simulating quantum computers. Okay? The future plan is actually having our Intel Spin qubit chip attached with the control electronics as well. So very from a high level, what does it comes, this system stack? there is one way to express your quantum application, quantum programs. In our case, we take the C++ language and then we extend it with quantum type, quantum operations. We heard in the first talks right today that there are codes that are 1 million lines. You don't want to write the same code for dedicated quantum devices. You just want to take the computational bottleneck and substitute this with quantum kernels. This can be done by keeping everything else in C. Then, of course, we have to extend the compiler. This is LLVM-based with quantum passes to be able to take care of the gate set, the connectivity, and so on and so forth. The quantum runtime is the way the host computer, the host CPU will talk with the quantum accelerator if you want, and also with mid-cycle measurements, right, active feedback, and blah, blah, blah. So the final backends, at the moment there are simulators, one very abstract, the other closer to the physics of quantum dots. We have a qubit control simulator as well, something to really kind of be able to simulate the pulses that come out from the electronics. In the future, as I mentioned, there will be some hardware available as well. So hit me up. We have some new release coming soon with features that we develop, but also features that the user requests. So there is a lot of interaction with the users. Thank you.
Hello, I'm Stefan from Parity Quantum Computing. Our company started from a very simple idea that in order to map spin problems, classical spin problems, onto quantum computers, instead of directly mapping the spins onto qubits, it's much more interesting to map the parity of spins onto qubits. Now, this turned out to have a lot of very interesting consequences, because it turns out that even if the spin problem has long-range interactions, on the qubit platform, everything becomes local. You only have to take care of nearest neighbor interactions. Now, we have to add some additional degrees of freedom and some constraints to that, but everything needed to implement this remains local. Another interesting aspect is that even we can do specific optimizations for very different kind of platforms, neutral atoms, superconducting qubits, spin qubits. There's a lot of specific things that all benefit from the same idea. Now, recently we also have developed a more universal approach using these same ideas. It turns out that a lot of circuits can be also implemented much more efficiently if you think in terms of parities instead of just spins. And so for that we have developed a whole software stack that is available online.
Shall I take 2 minutes, right? Go ahead.
Yeah, so we have you can download it to connect with our cloud service, which will map any spin problem onto a localized quantum circuit. You can export it to whatever platform you like. And we are working on further applications, so we also have now ideas how to map universal quantum circuits very efficiently. Please check out our poster if you want to know more. So, thanks a lot.
Thanks a lot.
Hello everyone, so I'm Nicolas Hortel, so a computer science PhD student, and so I'm here today to present you Perceval Quantum Software. So it was briefly introduced earlier, like about the full stack thing. So we want to connect for the high levels, so the client's algorithms, to the low levels of the quantum hardware. And so there are, so there are many quantum hardwares. So we are here focused on optics. And so now I would like to introduce Perceval. So it's basically the only operation support system dedicated to single photons. So now we present you some positive things about Perceval. So I would sound more like a seller rather than a PhD student. But here, so with Perceval you can design circuits, like any kind of single optical circuits. You can also simulate with very optimized backends in C and C++. And also, which is very cool, like it is connected to real photonic chips. So basically there is a cloud for over almost 1 year now, and you can run algorithm from that cloud. Also, it's collaborative and open source, so very cool also for software. So please don't hesitate to look at the code. And it's also connected to other software, because here it is photonic dedicated, but we also want to connect that to quantum algorithm, gate-based things like Qiskit, etc., etc. Also, I have a few seconds to talk about the hackathon we organized by Candela, so the company of Perceval. So in the middle of November, So please, you can go. There are many places, and we can also provide funding for people. And thanks. Please come to see the poster if you have any question about photonics or Perceval.
Thank you.
Hi, my name is Marius Schönloff. I'm a member of the German R&D team of Eviden, formerly known as Atos. There's also my colleague Michael Bauer in the room, and we have a poster on our Captiva framework, which is basically the quantum computing solution by Eviden. And the idea is that it's basically a complete quantum computing framework standing on a few pillars. Once we have a complete quantum computing software framework to define quantum algorithms. It's fine. To define quantum algorithms, then we have tools for circuit optimization and hardware adaptation, so compiling and stuff like this to map the actual quantum algorithm to the hardware which it is assigned to. Then we have, coming with our tool, a very powerful quantum emulator, such that you can test your algorithms before running them on actual hardware. We have easy user access handling, also for HPC integration. And last but not least, we have an easy way of integrating like every hardware. So they're basically hardware agnostic. The algorithms can be executed on all hardwares which are on the market, basically, when we have an easy interface. Yeah, so the idea is really that we have all software components here combined to define and execute quantum algorithms on real hardware. We also have some interoperability module that we can use other languages like Qiskit, Cirq, or other prominent examples, that users are not stuck with our way of defining quantum algorithms, and then you can actually basically run them on-premise or also as a service on the cloud, and you could choose between an emulator, so simulated hardware, or you can run it on a quantum computer. And in the poster we present, we will basically show you the software components of Captiva and also how we use them in current R&D projects. Thank you.
Thank you.
So, hello everybody, my name is Sebastian Zielinski, I'm from the QuEra lab of the LMU Munich. And today I'm going to present you the QuEra project, which is a research project funded by the German Federal Ministry of Education and Research. And our main goal is to establish a network and an ecosystem which is centered around the application of quantum computing. And I think as a researcher it's quite easy to oversee that quantum computing has of course very well made its way into the research and into the research facilities of big industry. But also there are smaller companies and SMEs that are struggling currently to adopt AI technologies or even with digitalization in general, and we are already throwing quantum computing at them. And this is where QuEra comes into place. So our goal is to establish the network and the ecosystem, and at the heart there is the QuEra platform. And here it's very important for us that we provide learning materials for people with various degrees of knowledge and provide solutions, code solutions that are free to use. And also there will be an access bureau, so you can directly contact us either virtually or you can physically come at us, and we will help you to realize your quantum computing or your use case that you're trying to solve with quantum technologies. Thank you.
Thank you.
Hi everyone, I'm Laurinas, I'm from QNSS. I will present a poster done by my colleagues and me, Shinya Onishi, me and Shota Takamoku. So, can we get the next slide? Here at QNSS we are working and focused on quantum software for chemical calculations. So our goal is a software which advances innovation in chemistry and material science field. So at our company we have a QLAC simulator and a QReparts library which enables composing and testing our algorithms. But with that we also wanted to go into the classrooms and try to see how people are receptive to the quantum software which are not quantum computing professionals. So we building a QuEra software which is based on web browser, and you can do currently simple things like ground state calculations. And our poster, I want to invite you to have a talk about how quantum software tools could be used in classroom, and also see a simple like intro or and survey study about what are the students' views on quantum software currently. Thank you very much.
So hello everyone, my name is Bao and I'm a first year graduate student at University of Delaware. So today I'm going to talk about my undergraduate project, which is qTritium. So for this project, I'm going to take you to a higher dimension space. So quantum qubit system, which is based on building system, is very famous in the community, in the quantum community. However, for the qtrit, which based on ternary system, it is not very famous. So we are developing a framework that can help you with, if you have an idea about the qtrit algorithm or a simulation task that is very native to the qtrit system, for example, neutrino oscillation, you can use this system to design and then decompose it into punts that you can run it on the IBM quantum backend. And we also try to expand it into into penny lane pulses that they just released, and maybe you can use that to do all kind of stuff. So that's all.
Thank you.
Hello, my name is Tobias Schmale. I'm here with my co-worker and supervisor Daniel Beuteling, who's also in the audience. We are from not the Munich Quantum Valley, but the other Quantum Valley in Lower Saxony, the QVLS. But we are also affiliated with a startup that was recently founded from QVLS called qDORA. And both of these entities are working on building trapped ion quantum computers targeting 50 plus qubits. And we are representing the software efforts at both of these teams. And on our poster, we want to highlight two of the projects that we are working on. On the one side, we want to show our compiler. By compiling, we mean mapping a circuit onto the ion device and solving the ion shuttling problem that arises at this step. And the other project we want to highlight is our vision for running hybrid quantum classical algorithms on this hardware. In particular, we want to make use of the coherence times of trapped ions, and we believe that it should be possible to run real-time hybrid algorithms simply by running an interpreted script, such as a Python script, in real time in parallel to the qubits while they are coherent. And we brought some numbers, some round-trip times, some latencies to back up these claims. And we hope by doing so that we can provide the simplest possible user interface for hybrid jobs without having to resort to any compiled, complicated new frameworks. And if any of these two topics sounds interesting to you, or if you have questions about QVLS or about qDORA, then feel free to meet us at our poster.
Thank you.
Hey, my name is Victor Moe, and I'm glad to be in Munich to talk about quantum software for the second time this year, thanks to Robert here. So today I'm going to talk about SuperStack, which we just publicly launched 2 weeks ago. And what SuperStack is a compiler that uses underlying hardware information to get 10x gains on circuit performance. So for now we target like superconducting ion trap and neutral atom systems. And the techniques we apply, dynamical decoupling, bring your own gate set, where we compile to a device's native gate set instead of compiling to an ideal gate set, and global gate decomposition for neutral atom devices. As you can see on the bottom left, we run dynamical decoupling on an IBM device, and we get, you can see that the number of counts is higher than just if you submitted your circuit to RockSKit. This was done on the Bernstein Vazirani circuit, by the way. So SuperStack has customers, Advanced Quantum Testbed at Berkeley, QSCAD at Sandia, maybe year, hopefully. And yeah, if you have any questions, you can come talk to me at my poster or contact us at superstack@infection.com.
Great, thank you.
Hey, my name is Jacob. I'm going to introduce the tequila package, which we're developing at the University of Augsburg. It's as far away from the Munich Central Station as this campus is, so it's pretty close. And what it basically is, to make it short, it's like an abstraction framework which you can use as a test bed if you have new ideas. So it's designed for rapid prototyping. Although if you want to simulate something it's not that slow actually in the end. And the main idea is you take one data structure, a list of expectation values and a general transformation of what you would do with them after you evaluate them. And then you make it in a way that every type of operation that you would do on this data structure results in the same data structure. And next slide, please. And this is just a small example how you can represent something that looks fairly complicated. You say you have a circuit, a Hamiltonian, then a relatively complicated function, and then you're taking this function and use it as an input to another circuit, another Hamiltonian, another function that's somehow transformed. And the question would be, how would that function look like? And in the blue boxes, you basically see the code and how you can initialize this. And it's hopefully to illustrate a little bit that it can be quite easily be done on a high level perspective. If you're interested, we have a poster with some applications in real science. And thanks.
The last presentation is just a little bit different. As you know, everyone in public universities are dependent on public funding, and of course we're happy to give whenever possible the stage also to our funding agencies. So here you go.
Thank you very much to letting me pitch in this session, even without a poster. So I'm here to mention that quantum software is also in the focus of the Federal Ministry of Education and Research. We have already had 2 calls covering this topic in the last years, and it's also part of the REACHES program, Quantum Systems. And to get a little bit closer, what topics are in focus within this program is quantum simulation, machine learning and optimization, quantum algorithms for non-gate-based quantum computing, hybrid algorithms for co-processing in the HPC environment, and much more. How is applied coupling into these topics? In our case, is that all these topics are defined around a use case. How would typical funding look like for one of these topics? It would consist of a focused consortia consisting of companies, universities, and research facilities. And due to the low maturity of the maximum funding rate of 80% is possible. And of course, in such a project, the economic exploitation must be within the European Economic Area. If you want to have further information, you can contact me or my colleague, Mr. Lachner, and we are happy to give you more information, and you can find our business cards behind these QR codes. Thank you very much.